Today we'll be looking into the concept of uh, system software. So system software has 5 modules, and the first module is all about the introduction about the system software and machine architecture. So here we speak about the introduction, what exactly the system software is, and how to deal with it, and how they are created, how they are written, how they will work. And we also look into the architecture of previously available system software. And what is this SIC? So SIC stands for Simplified Instruction Computers, right? So about the SICXC, what are the architecture of SIC machine architecture? And we also have something called as extended version of SIC XC and that architecture, and some of the examples of it. So to start with, we deal with the concept of software. So what exactly is the software, and why it is very much needed, right? The term software refers to the set of programs, right? So set of program instructions. So we have some instructions, some small tiny set of codes, some statements which are put together to do some particular task is called as a software. So what do you mean by hardware? A hardware refers to it's a physical component. It's a feel like device, right? It's a feel like device where you can feel it, you can touch it, right? So you can see and touch. And for example, our pen drive or the hard drive have the mouse and keyboard. They come under the term hardware, right? And the software cannot be felt; it can only be seen. It can only be imagined, right? Hardware is nothing but you can feel and touch, right? So next is the two parts of software. One is the application software, and the other one is system software. So application software are the particular set of codes which all of your apps which are running on the top side of the top layer of any given architecture is called as a application software, where you can see over here, right? So this is the top layer. So below that particular application software, we have another software, something called as system software, right? Below that, we have the hardware. So hardware is very essential. So that's the central core part, right? That's the hardware. On top of it, we have the system software. On top of it, we have the application software. One thing which you have to understand here is what are the things that application software will take care of. So it takes care of, basically it's the creamy layer where we have the user, right? So the user will interact with the application software. User via the application software interacts the system software. User via the system software will be able to access the hardware. This is how the hierarchy actually goes off, right? So what are the things which we actually learned here in the application software? So applications like spreadsheets, your Excels, gaming applications, some databases, some browsers, right? So they all come under the application software. So what are the things that comes under system software? Things like operating system and some libraries comes under the system software. In system software, we also have something like linkers, loaders, assemblers, right? So compilers, right? So they all come under the system software. So the inner core is our hardware, which is our CPU as well as the CPU as well as the mouse or the pen drives or the hard drives or the RAM, ROM, processor. Everything comes under the hardware, right? So that will be the relationship between the system software, application software, and the hardware. So the particular definition of system software goes in this way. A system software is a set of programs that are dedicated to manage the computer itself, such as I told you here, operating system and uh, such as operating system and some file management utilities, right? So application software are a set of productivity programs or the end user programs to perform that specific task, right? So yes, when we speak about any of the application, it will be on top of the system software, right? Via the system software only it can gain the access of any of the particular hardware, right? So this we have to understand. So next comes the difference between the system software and the application software. So the system software um, is a set of programs that are dedicated to manage the computer itself. What about the application software? It's a set of programs dedicated to permit the user to perform a certain task. So what about our system software? It is mainly written in assembly language. The higher level language is written in higher level programming language, such as C, C++, Java, and etc. It just goes on. So application program runs as when the user wants, when the user requests, but the, the system software will run whenever the system is turned on, whenever the computer itself is turned on. So it will be keep on running unless until the system is shut down, right? So next comes the system is unable to run without the system software. Yes, that is true. Applications, the software is not required to run the system if with respect to the user specific, it is specific to user. It is related the system software where the OS itself is dealing with the system software. Yeah. So system software is a general purpose. So what about the application software? It is specific purpose. Right. So what are the things that will be taken care of? I told you that operating system, assemblers, compiler, loader, linker, text editor, debugger, macro processors, they all come under the system software. So the web browser, word processing, spreadsheet, database, all those things, games, they all come under something called as application software, right? So our system software is machine dependent. That is our hardware dependent. So application software is not machine dependent. So this is one thing which you need to understand. Okay. So next we speak about the concept of the architecture, right? So the architecture of system software. Uh, yeah, the common thing of system software, as we just saw, one thing is system software is machine dependency. System programs are intended to support the operating system. They are supporting the operation and use of the computer. So machine architecture defines or differs in the machine code, in the format, in the addressing mode and registers. So these are the changes when we see with respect to the system software, right? So majorly here we speak about the SIC, Simplified Instruction Computer, and how exactly that is. Machine independency of system software majorly will take care of the design and logic, code optimization, and subprogram linking. Next. Next comes our SIC. So as I told you, SIC stands for Simplified Instruction Computers. So what do you mean by simplified instruction computers? Over time, we had many problems, right? It was very difficult to study um, the architecture. Later, the different systems came with different features, right? To avoid the problem, we actually came with one particular architecture, which was a fixed architecture, right? Where we wanted to maintain a standard. So that's where we have the simplified instruction. computer. And yes, SIC is a system which is introduced for the system software. So most of the modern microprocessor actually include the complex function for the process of efficiency. It is very difficult to learn the system software using a real world system. So the simplified instruction computer solve this problem by abstracting away this computer behavior in favor of the architecture. So yes, so I told you SIC comes with two versions. One is with the standard SIC, and the other one is another one is extra equipped or extra expensive version. That is SIC XE version. The two versions has been designated to be the upward compatibility, meaning any new software or any new upgradation will support the older one, or the one which we have written will support the next upcoming design also. So this is called as upward compatible. So next, what are the things that comes under SIC? So SIC is where this architecture mainly takes care of the memory, takes care of the registers, data formats, instruction formats, address formats, addressing modes, instruction set, input and output. So looking into the first term here, first is the memory. So SIC memory is about 8 bits, right? So 1 bit is nothing but it is either 0 or 1, right? So similarly, the memory with respect to the SIC is about 8 bit. Any 3 consecutive bytes will form a word, right? So 8 bit is actually 1 byte, right? So 3 bytes refers to how much? 3 into 8, that is 24 bits, right? So 3 byte will actually form a word. All address on SIC are byte addresses. Words are addressed by the location of their lowest numbered byte. Okay, so words are addressed by their lowest address byte. So overall, we have the memory of 2 power 15, that is 32,768 bits, right? Yeah, 32,768 bytes of memory space for the overall. So as it is to 15 power, we can take care of 15 line address buses. So how much registers we have? SIC has 5 registers and all have their special uses. Each register is about 24-bit in length. Table shows the mnemonic number and uses of the particular register. So what is the table? This is the table, and here, so the 5 particular uh, registers are, we have register A, which is standing for accumulator register. The number for this particular register is 0, used for arithmetic operations, meaning addition, subtraction, multiplication, division, modulus. So next comes the register X, which stands for index register. The number is 1, used for addressing. So we have the contents of the address, which should be added with the index register contents to go to the memory location. Next, L stands for the linkage registers. The number is 2, where the linkage register is used when you have to move from one function to another function. In other words, it is called as a subroutine instruction, which stores the return addresses. Next comes the fourth one, which is our PC register, meaning the program counter register, and the number is 8. So what does this PC holds? It actually contains the address of the next executable instruction, which has to be fetched for the next execution by the processor. Next, fifth register is SW, which stands for status word, and its number is 9, right? So contains the variety of information, including the condition code in the comp instruction. So these are the 5 different. You may be wondering, where did 3, 4, 5, 6, and 7 numbers went? They all will come in the extended version. Okay. Yes. So data formats. Data formats is where I told you that we have, it's a 24-bit binary number. Integers can hold 24-bit binary number, and meaning it is starting from 0 to 2 power 14 minus 2 power 24 minus 1 with respect to the negative, right? So negative values are represented with respect to what? We know that it's 2's complement. So minus 24 is represented as, so first we take one's complement and add one to the one's complement of any number to get the 2's complement. Okay. So 24 is, this is 1, this is 4, this is 8, and this is 16. 16 plus 1 is, sorry, 16 plus 8 is 24, right? So how do I get minus 24? One's complement of 24. So this is 1, 1, 1, 0, 0, 1, 1, 1, and adding 1 to it, we will be getting 0, 0, 0, 1, 0, 1, 1, 1 will be the value for 2's complement. So that's how the data formats will actually be taken care of, right? Characters are used to save in 8-bit ASCII code, right? So why 8-bit? We actually need 8 bits to represent any of the character. It can be a character, so a character will have a single quotes, right? So 65 will be the ASCII code for A, and 96 will be the ASCII code for the small a. Okay, so this by basics you will be knowing it. So the characters are stored using their 8-bit ASCII codes. There is no floating point hardware in the standard version of SIC. This one has to be knowing it, right? In SIC, we do not have floating point hardware on the standard version of SIC. I mean, it cannot calculate the decimal point values, right? And next we move on to the instruction format. I told you it is 24-bit addressing, right? So instruction format will be 24 bits. So the particular SIC standard version is 24-bit, and this is how the instruction format is taken, and it has been divided into 3 components. One is for the opcode, one is for the index, one is for the address. As you can see, 8 bits are reserved to store the opcode, 1 bit for storing the index, whether index to be added or not. If it is 1, we need to add it. If it is 0, we don't need to add it. That's what it says. So address should be of 15, is of 15 bits. We saw that we have 15 address lines previously, right? So 15 bits are used to store the addresses. So if I told you that if X is highlighted, then it is index addressing mode. If not, it is just normal addressing mode. Okay. So we have certain types of addressing mode. We look into how many types of addressing modes we have. So the first is the direct addressing. The direct addressing is where the index will be 0. Index addressing is where the X will be 1. So how do I calculate the target address, which is our TA? So TA address is basically the same address what we have, meaning whatever the address what we have over here, that will be the target address if this X bit is 0. Okay, so that will be the direct addressing. What will be the indirect addressing or the index addressing? The index addressing will actually be having the contents of X which will be added. The contents of X will be added. If X is equals to 1, the contents of X plus the address will become my target addresses, right? So we can just see one example here. So any instruction, I told you in SIC, any instruction in SIC, 8 bits is for the opcode, 1 bit is for the index, and 15 bit is for the address, right? So load into accumulator is having the opcode as 00. This will be available in a chart. These values, opcode values, will be available in the chart. So don't worry, in your examination, the particular uh, the paper setter will give the value of LDA or whatever the opcode which he actually takes for this particular instruction. Okay, so LDA 10 we have. So we have the opcode as 00. That is the opcode for 0 it is 0, and another thing it is 0. And one more thing which you need to understand is this is a hexadecimal number, right? That's why you have 4 bits for two values. And this is not an indexed addressing. So the X value will be 0. And another thing is this is a memory address. So in the memory of 10, there is 1000 which is actually given. This is also in hexadecimal. So this is 1000, right? So 1000, as it is not an index, you don't need to add the contents of index register. So it is straight away the address which will be my effective address or target address. I hope you understood. Next, we have the concept of index register. So how does this index register work? I told you that whenever this index bit is 1, whatever the contents which we have on the index register will be added. This is what is added. So 1000 plus the contents of index register will be the value or my target address value. So next is the instruction set. So in the instruction set, we have instructions related to load and store, right? So load and store, LDA stands for load into accumulator, LDX stands for load into index register, store into accumulator, store into index register. Okay. So integer arithmetic operations. I told you the arithmetic operations are add, sub, multiplication, and division. Arithmetic operation involves two register. One is A, the register A, and a word in memory that will be result from left in the register. For example, add word refers to accumulator register plus the particular memory location will be loaded into the accumulator, right? So that's the instruction example. Comparison is whereby we use the comparison instruction as comp. So what does this comp say? Comp actually says that compares the value of register A with memory and sets the condition CC accordingly. So CC is conditional code. So if it is less than or greater than or equal to, that value will be actually stored in the CC. Okay. So that's the comparison operator. Next is about the conditional jump instruction. So jumping based on some condition, I have to move from one function to another function. So the condition, if it is lesser than, if it is equal to, and if it is greater than. Jump is lesser than, jump is greater than, jump if equal to. These instruction will actually tell the setting of the status and jump accordingly. There are subroutine instruction, jump to subroutine and return from the subroutine. So JSub stands for jump to the subroutine, jump to the function by placing the return address on the register L. That is your linkage register. RSub is returning by jumping to the address contained in the register L. Wherever you what contents you have in L, To there you go. Function to the caller. Okay. So next is you have, for example, yes, the understanding here for RSub. So we have the main function. This is the calling function. This is the called function. So what happens? Add of 1 comma 2. So now I am going to the subroutine of add because add is the function. So what it does, it puts some value in the linkage register, meaning where I actually stopped. So it goes here, add, get the value, it works all the job, and now it is coming back. This is called as return. So what happens when you return? The contents of linkage register will be taken back and it knows where exactly to come back. So that's how the linkage actually works. So next, yeah, mainly the linkage will be stored in the stack. The top of the stack will be saved, and when you call the add method, that particular address, the next executable address will be pushed into the stack. So once it is done, the return address, once the return is performed, the stock happens how to go back to the caller based on it will just pop the contents so that the value will be the last address where it has to move, right? So next is about the input and output. We should be knowing that SIC also supports the hardware meaning input and output. So moving of data from one place to another place, right? Whether it can be getting the input or putting or sending the data. Getting the data is input, and uh, displaying the data or pushing the data is called as output. Is performed by transferring the 1 byte data at a time, right? 8 bits of information at a time, or from the rightmost 8 bits to the register A. So accumulator register takes care of all the input and output. Each device is assigned a unique 8-bit code. There are 3 instructions which actually work on the device. The first is the test device, or the instruction is called as TD. TD stands for test device, meaning whether the device is present, ready to use, or not ready to use. These information I need to know. So how do I get to know this? If my condition code in the status word register is lesser than, then the device is ready to send or receive the data. If my status word register, the condition code is equal to, then the device is not ready, don't send the data. Okay, a program has to wait until the device is ready, then execute the, yeah, when it comes to the input, it is the read, and when it comes to the output of data, then it is write. Next comes the sequence should be continued for each byte of data of IO. So transferring 8 byte of data from the input source into the rightmost of register A, and WD is the word byte of data is loaded into the rightmost of register A and then returned to the output device. Okay. So next we have the particular example. So SIC instruction for this, we'll look into this particular concept in the next class. Any doubts?